Hello, I welcome you all in this course of Refrigeration and Air Conditioning. Today we will cover the concluding part of vapor absorption systems. In vapor absorption system, today we will be covering thermodynamic requirements of mixture, 3 fluid absorption system that will interest you, comparison between 2 fluid and 3 fluid absorption systems, and we will work out some examples. Properties of ideal refrigerants. In vapor compression system also we discuss the properties of ideal refrigerants. Now here in the absorption system also there are certain desired properties of an ideal refrigerant. Now vapor pressure at the condenser and evaporator pressure should not be far from atmospheric. That was also requirement in the vapor compression system, that the pressure in the evaporator and condenser 1, 2, 3, 4. So this is evaporator and this is condenser. So pressure should not be far from atmospheric because the pressure, when pressure is far from atmospheric, whether it is high pressure or low pressure, that causes problem, because the pressure is high, then system has to be robust. And if the pressure in the evaporator is very low, in that case the specific volume of the vapors emerging at state 1 will be very low. Specific volume is meter cube per kg. So if 1 kg of refrigerant is in circulation, if evaporator pressure is low, then volume will increase and compressor will have to handle high volume of the gases, or the size of the compressor will be larger. So either way, pressure should not be very high in the condenser and should not be very low in evaporator. So pressure, it is the ideal case is the pressure in the entire system is slightly above the atmosphere. So pressure in the evaporator is slightly above the atmosphere and pressure in the condenser is not very high. That is the very comfortable situation. The refrigerant has to be in any case chemically stable during the process. Critical temperature should be high. Critical temperature means temperature at this point. Farther you are operating from critical temperature, higher is the COP of the system. Same is the case in absorption system. So critical temperature, so the cycle should operate far away from critical temperature. Large latent heat of vaporization, if there is large heat of vaporization for the same amount of heat transfer, less amount of refrigerant shall have to be circulated, and definitely we can go for smaller size of a compressor or a pump in absorption system. In any case, if the latent heat of vaporization is high, we will have to handle, or the system will have to handle, small amount of refrigerant, and that is always desired. Low specific heat, because if the specific heat is low, high specific heat means that more energy will go in the form of sensible heat. So in any refrigeration system, it is not recommended that the considerable amount, especially in the vapor compression system and absorption system, that considerable amount of energy goes in the form of specific heat. That is why the system should have low specific heat. Now properties of an ideal absorbent. So absorbent should remain in liquid condition during the operation. During the entire operation, the absorbent has to remain in liquid condition. However, you must, last time we discussed about the liquid, this water ammonia system, where traces of water were going with the ammonia. That was not desired. That is why a rectifier was used to condense the traces of water vapor and drain them back to the generator. Now absorber has to be chemically stable in the entire range of operation. It should have high boiling point, low specific heat. Heat liberated during the absorption should be minimum. So during absorption process, the heat liberated should be minimum because this is the heat loss from the system. Now mixture, the properties of mixture, properties of absorbent and the refrigerant. Solubility should decrease with temperature. That is always desired, because in absorber the refrigerant is absorbed at lower temperature, the pressure of the refrigerant is increased through a pump, and then the mixture is heated in generator. In generator, the refrigerant is liberated, definitely the solubility of the refrigerant reduces in generator, or it is required to be reduced in generator. And that is why it is stated here, solubility should decrease with temperature. So when we increase the temperature, the solubility of refrigerant should decrease, otherwise we will be losing this effect, refrigerating effect. Chemically stable, the mixture has to be chemically stable, it should not react at any temperature. refrigerant should be more volatile. So, refrigerant should be volatile so that easily it can be converted into the vapor. So, where refrigerant is required to be more volatile, it has to be non-corrosive, that is obvious. A fluid which is in the system has to be non-corrosive, whether it is refrigerant or an absorbent, non-toxic, non-flammable, this is requirement. That is why, because ammonia is toxic. So, that is why ammonia cannot be used directly as a refrigerant. So, ammonia refrigeration system will again used a secondary refrigerant for providing the necessary cooling, because ammonia, for especially for the public uses or where the food stuff is stored, in the cold storage where food stuff is stored, the use of ammonia is avoided. Difference in boiling point between of refrigerant and absorbent should be around 200 degrees centigrade. So, that we find in the case of lithium bromide water refrigeration system. That is why in that system we do not require any rectifier, and when heating of refrigerant takes place inside the generator, only water vapors are generated. So, this is the property of ideal mixture. Now, we will come to the a different type of refrigeration system, which is known as 3-fluid refrigeration system. This system was recommended by undergraduate, not recommended, it was developed by the undergraduate students in KTH Sweden. So, these two undergraduate students, they proposed this system, and in this system there is no moving part, it is completely silent system, and pressure in the evaporator is controlled with the help of hydrogen. Hydrogen is another fluid. So, it has 3 fluids, that is why it is known as 3-fluid system. Water is absorbent, there is ammonia which is refrigerant, and there is hydrogen which is a driving fluid. In low pressure side, it is a mixture of hydrogen and partial pressure of water, partial pressure of ammonia, and partial pressure of hydrogen. In high pressure side, low pressure side means in absorber, and high pressure side it is partial pressure of water and partial pressure of ammonia. So, hydrogen is confined to the low pressure side, and total pressure of the system remains constant. Now, I will draw the schematic of the system, and the working of the system will be clear to you. So, we will start with the generator. So, there is a generator which is at Tg, and heat is given to the generator. In the generator, the mixture of vapor and liquid, it is transmitted to separator. There is a separator. After generator, there is a separator where stratification of liquid and vapor takes place. Now, in this case, the vapor goes to the condenser. Now, after condenser, it is connected to evaporator. And from evaporator, expansion takes place, it comes to the, expansion takes place before evaporator. So, expansion takes place here, and then it goes to the evaporator, and from evaporator it goes to the absorber. And this is absorber. System is not complete yet. Now, this absorber is not connected to the generator here. Generator, now heat I will show with the red one. This is heat is going here. So, absorber is not connected to generator. It is connected to separator. This is separator. which this is a generator. So, here when the ammonia vapor leaves the separator, we get weak solution, and weak solution from here it has to be drained back to the absorber. So, weak solution is drained back to the absorber. Now, this is a peculiar type of arrangement I am doing here, and if you look at the PPT, you will find a better arrangement. It is the same arrangement done here. Now, liquid from separator, this is weak solution. It here it is drained back to absorber. Now, what is the function of hydrogen here? Because we have to maintain here pressure difference on high pressure side and low pressure side, and expansion valve is already provided here. Okay. Now, in this system expansion valve is not there, it is expansion valve free system, expansion valve is not here. Hydrogen is confined to this area. So, hydrogen is confined to this area and it is a driving fluid, and so it is liberated here. It takes heat from the weak weak solution of ammonia in water, and it moves in this direction. It goes here, and in order to maintain the pressure in the system, it drains back to the absorber. So, this is the circuit for hydrogen in the vapor absorption system, and we have to maintain high pressure and low pressure side. So, the difference is very less, but here in order to avoid that hydrogen does not escape in this direction, a vapor lock is provided. A vapor lock is nothing but we simply bend the tube so that vapor cannot enter this side. So, hydrogen is confined to this side, this is hydrogen. Hydrogen is confined to this side and it does not enter here. A vapor lock is also provided here so that it does not enter on high pressure side from this channel. So, here one vapor lock is there, here another vapor lock is there, hydrogen is confined to this side, and evaporator, the total pressure in the evaporator will be the partial pressure, which also include partial pressure of hydrogen, partial pressure of ammonia and partial pressure of hydrogen, and Dalton's law of partial pressure is applicable here, and that will give the total pressure in the evaporator. Now, here in separator, the movement of the fluid, this is the heated fluid, this is in generator, the liquid and bubbles, the vapor bubbles, they move together in this channel and they come to the separator, and the weak solution is drained back to the absorber from this point. So, this is the entire circuit of a 3 fluid system. It appears to be a little complicated because there is no moving part, there are no valves, only vapor locks are there. Now, suppose I will give you another example of how these vapor locks are effective. Suppose in a pipe, in a horizontal pipe, it is altogether different problem related with the fluid mechanics. Suppose in a pipe, I want to ensure that during the flow the pipe is fully flooded. I mean, there is no vapor or air in the pipe irrespective of the flow rate. Normally what happens when the flow rate is low, there is a tendency for stratification of the flow. But if I provide U-turn here, in that case a U-bend will always ensure that the pipes are fully flooded at any flow rate. Similarly, if I put a bend here, under any circumstances hydrogen will not be able to escape through this passage. Similarly, here hydrogen will not be able to flow through this package and it will be confined to the low pressure side. And during the process, the hydrogen takes heat, becomes lighter and it moves in upward direction, and subsequently it get mixed with the ammonia and it moves in the downward direction. So, it is a driving fluid in the 3 fluid system. Now, in this type of system, since there is no moving part, it is absolutely silent. If there is no moving part, it means external energy is not required in the system. Once external energy is not required in the system, it means simply if I provide heat, some heat is available here, or if you go for these type of refrigerators, because Electrolux is a company which used this concept and develop number of, they went for the mass production of Electrolux refrigerator working on the 3 fluid system. So, in this system, it is very good for the rural applications where there is no electricity. You simply heat the generator with the help of a candle, maybe some waste heat is available if in the rural area, and in the refrigerator in the morning, in the evaporator, you will get the ice. So, it may sound very strange to the villagers that you are burning some leaves or some cow dung here and you are getting ice in the evaporator. So, it has immense applications in the area where the electricity is not there. On the other side, the cost of this system is high. The cost of this system is high and it has to be handled with very care. It has to be carefully handled. Otherwise, the mixing of fluid will take place. The moment hydrogen enters this side, the system will not work at all. So, comparison between 2 fluid and 3 fluid absorption system, if we compare this with the lithium bromide and water ammonia type of system, this is silent in operation. I have already explained you. The cost, this system, the 3 fluid system is slightly costlier than the 2 fluid system. The pressure inside the system is, variation in the pressure is not very high. Variation in the pressure is not very high in this system from evaporator to condenser. Lubrication is not required because there is no moving part. Lubrication is not required and this type of system is maintenance free. But the major drawback of this system is that the cost is high. Perhaps if we go for the mass production, cost can also be reduced. But this is very good, this type of refrigerator is very good for the rural applications where there is no electricity. Now, I will take one example to understand the working of an absorption system, 3 fluid absorption system. For Electrolux refrigerator, the evaporator temperature is minus 16 degrees centigrade. So, evaporator temperature is minus 16 degrees centigrade. And the condenser temperature is 40 degrees centigrade. So, T condenser is 40 degrees centigrade. So, minus 16 will be 273 minus 16, 257, 257 Kelvin and this is 313 Kelvin. Determine partial pressure of hydrogen in evaporator, because evaporator will consist of hydrogen. So, here in this case we have to find the partial pressure of hydrogen. The system pressure is equal to pressure at ammonia at 40 degrees centigrade. Why? The total system pressure is the pressure of ammonia at 40 degrees centigrade, because in condenser where temperature is 40 degrees centigrade, there is only ammonia, that is anhydrous ammonia. It means there is pure ammonia which is existing inside the condenser, and when it is getting condensed, it means saturation pressure at 40 degrees centigrade is the total pressure of the system, and the total pressure of the system is ammonia at 40 degrees centigrade, and that is 15.554 bar. So, ammonia is condensing in the condenser at 15.554 bar. Now, if we go to the evaporator, case 1, partial pressure of water vapor is neglected. Now, in evaporator we have total pressure in the evaporator is equal to the pressure of ammonia plus pressure of hydrogen. But it is not this pressure, this is at 40 degrees centigrade. Evaporator temperature is 257 Kelvin. So at minus 16 degree centigrade, the pressure in the evaporator of ammonia and hydrogen will be the total pressure. Now the total pressure of the system is 15.554 bar, right, and that is equal to pressure of ammonia at minus 16 degree centigrade, pressure of ammonia at minus 16 degree centigrade is 2.263 bar, pressure of ammonia at minus 16 degree centigrade. Now this is equal to, so the pressure in the evaporator of hydrogen at minus 16 degree centigrade is going to be total pressure 15.554 minus 2.263, and that is going to be equal to 13.291 bar. This is the partial pressure of hydrogen in evaporator. When water vapor is neglected, now suppose we consider in actual system there are water vapors also. Now if we consider the water vapor, then in condenser there is not going to be pure ammonia, it is going to be the water vapor also. So partial pressure of hydrogen oxide, that is water, shall have to be included, that is 0.0738 bar. So at 40 degree centigrade, the total pressure of the system is not the pressure of ammonia, at it is pressure of the ammonia, partial pressure of ammonia at 40 degree centigrade, that is 15.554 bar, and because traces of water vapor are also present, so the total pressure will be partial pressure of water per partial pressure of ammonia. And if we add these two, 0.0738 plus 15.554, and that will give the total pressure as 15.6278 bar. Now the total pressure of the system is going to be this much. Now with this total pressure, if I remove the pressure of ammonia, I will get the pressure of water. So pressure of water is equal to total system pressure minus the partial pressure of ammonia. So total pressure is 15.6278 minus partial pressure of ammonia at minus 16 degree centigrade, and that is equal to 2.263, and that will give the partial pressure of hydrogen 13.3648. So with the presence of traces of water in the system, the partial pressure of hydrogen in the evaporator has slightly increased. So we have completed almost so today we will be finishing the refrigeration systems, and next class we will start with the air conditioning systems. In refrigeration systems we have covered air refrigeration systems, we have covered vapor compression refrigeration system, we have covered multi pressure systems, multi evaporator system, multi compression systems, and the previous including this lecture, in these last three lectures we have covered vapor absorption system, and we have covered water ammonia type of absorption system, lithium bromide water system. Anyway, in the next class we will start with the introduction to air conditioning. Thank you very much.